But what I'd like to really, hopefully in the context of this talk, you'll understand about why we talk about 1 billion watts. And that theme will be hit a lot here. But first, I actually wanted to put some pictures about on the cover of people and things that Don Gurnett really loves. Obviously, his family. I couldn't help but grab this picture. This is just an adorable picture with his daughter and with his sailplane. Right? That's just an awesome picture. Of course, is that Suzanne? Of course, his fantastic work. And then, of course, auroral radio emissions. You love those too. So, yeah. So we hopefully got everything covered here. I was actually a student here at the University of Iowa. And actually, I'm going to be talking about activity in the late 70s to throughout the 80s. Actually a rather culturally curious time with the advent of disco and Animal House, the movie, and Saturday Night Live. But hopefully we got our physics story straight here. But I was actually, Don taught me in 8 undergraduate courses, I believe. I think you taught me physics 1 and 2, electromagnetic theory 1 and 2, plasma physics 1 and 2, and actually you were doing a dry run on your book because you actually had the typewritten manuscript, and actually advanced research 1 and 2. I recall at the end of semester 1 you gave me a good talking to about how I had to kind of pick up my pace a little bit. And of course you were my advisors on my master's and PhD thesis, and even now we work together on the Cassini team. So you've been sort of a presence in my life for quite a while. There's a funny story with that, believe it or not. I was the only person from New York, so I actually had a social security number different from everybody else at Iowa. So everyone always knew my grades, even though you put them up from social security number. Yeah, so it was pretty funny. But one thing I want to mention here is I'm going to talk about Don, not just through my own work, but through other students. And actually, people may remember the old UNIVAC computer. That was actually the equivalent of our water cooler. I mean, because it was a serial computer. You could only run program at a time. We all waited in line, and we just talked about what we did. And it was through those interactions that we got to, I particularly got to learn about Don, and not only through my own work, but how you were thinking with everybody else. So that'll be a theme, and it'll hopefully talk. Now, to start this talk, I want to go back back 60 years. And there's a plaque on River Road in western Montgomery County in Maryland, where investigators Bernie Burke and Ken Franklin first made the ground-based detection of a radio emission at about 22 megahertz at Jupiter. And they did this with a 96-acre antenna array. And this is sort of an interesting plaque because it's really the start of a new science called Planetary radio astronomy. Now, actually in 1955, and I would say all the way up to 1974, they couldn't call it planetary radio astronomy. They could only call it Jovian radio astronomy. But the distinction is that in 1974, you actually knew that there was more than one planet that could give off a radio emission. I'm going to hopefully talk about that because I think discoveries made by Don Gurnett actually started this whole field and moved it not just beyond Jupiter, but to all the planets with strong magnetic fields. Now, I just want to talk a little bit about Jupiter itself. Burke and Franklin made the discovery back in 55 in the tens of megahertz. Actually, it was found that these radio emissions from Jupiter, they're like a searchlight, and they rotate around. You can actually figure out the rotation period of Jupiter. Theorists also thought that maybe this radio emission was emitted at the electron-cyclotron frequency. And I think Don talked about this as electrons spiral down magnetic field lines. These spiraling electrons can generate radio emission. And what's really nice about it is if you know the frequency of the radio emission, you can actually infer the magnetic field of Jupiter. So people were remote sensing the magnetic field strength at Jupiter before Pioneer 10 got there to confirm their magnetic field inferences. Part of this emission from Jupiter was also modulated by Io, and so there's not just a regular decametric radiation, but this Io component as well. And again, given that it was at the electron-cyclotron frequency, you can sense the Jovian magnetic field. It's a great way of sensing magnetic fields. So early 1970, 1974, discovery at Earth of another radio emission. This was Don's paper Earth as a radio source, terrestrial kilometric radiation, and is this is really a radiation that you would detect in your AM radio band. The thing is, it's blocked by the ionosphere. But in fact, if this was allowed to get through the ionosphere, this would really disrupt your AM communications. This emission was actually strongly correlated with auroral activity. So this is a ground-based magnetometer, and when auroral activity peaked up, when the aurora brightened up, you could see this radiation brightened up as well. What's amazing about this is where the billions of watts comes in. This naturally occurring radio source had 1 billion watts of power. And actually about 1% of the aurora dumped its energy into this radio emission. By comparison, the strongest AM radio channels, radio broadcasts were about 500 kilowatts. So it's nearly 2,000, factor 2,000 difference between the two. And these observations were made actually with the IM6 interplanetary monitoring platform, IM6 and IM7, using spectrum analyzers, not unlike what Don was showing over here, these 16-channel spectrum analyzers. So here again is auroral kilometric radiation, and this is an Air Force satellite passing at low altitudes looking at the aurora, and you can see the AKR, this or terrestrial kilometric radiation. When there was no aurora, you wouldn't see it, but when the aurora peaked up, you could actually see the emission. So the connection to the aurora was pretty profound and distinct. Now these studies were backed up by a set of Hawkeye 1 studies. Now Hawkeye 1 was actually a spacecraft built here at Iowa. It had a magnetometer, a plasma particle sensor, and one of Don's spectrum analyzer. And Bill Kurth in '75 started formally calling this auroral kilometric radiation. So the name moved from terrestrial kilometric radiation to auroral kilometric radiation. And Bill also did a nice set of direction finding studies and found that the source had to be relatively near Earth. Now Jim Green, who's right here in the audience, also did like 3 papers on auroral kilometric radiation. And actually he found that if you put a source relatively close to Earth and have it beam out, he did some ray tracing and connected this source to magnetic field lines that were going out into the night side, you could replicate the distribution of the emission. So there's basically a body of literature coming out of here indicating that this is an auroral radio source, really strong, near the foot of the magnetic field lines that extend nightward, about 70 degrees in variant latitude in the auroral region. So the question is this similar to decametric radiation at Jupiter? How close is that? But not everybody was on board with this. And I call this Don Gurnett versus the government. And there was a group at Goddard, the Outlaw Don, we can call them that, Outlaw Don, for about 5 years. And Bob Stone and the Goddard group sort of had a different view of all this using Radio Astronomy Explorer 2. And they just did not think that this was an auroral source. And in fact, they had 4 papers. They actually had a series of papers called Terrestrial Kilometric Radiation. And you can see this is and I should also, full disclosure here, I moved from Iowa to Goddard and was Mike Kaiser's postdoc. So I've heard both sides of this story. Roger Anderson is the one who presented to me first, and Roger, of course, always had really an interesting way of expressing himself, which is a lot of fun. And of course, Mike always has his way of expressing himself about this. Actually, they ended up not being that different, though. But you can see here, this is the equivalent of, I would say, scientifically talking smack. They didn't talk smack, but if you read what the quote here, one semantic note is in order before beginning. After Gurnett introduced the term terrestrial kilometric radiation, Kurth presented strong arguments that would favor the more specific name, auroral kilometric radiation. As a result of our study, we'll show, however, it is still not completely clear that all the observed emissions are strictly auroral. Therefore, they prefer to continue to use the name TKR. So it's TKR versus AKR. This is sort of where we're at here. Of course, they just didn't do this just to be petulant or contrarians. They actually had some analytical proof here. And here's what they had. RAE, Radio Astronomy Explorer, was at the moon. They actually had 2 229-meter V antennas, fully extended. This thing was the length of the Empire State Building. And what happens is when the moon would actually occult Earth and the AKR sources, and you can actually see the sources turn off. And so they were getting radiation sources well away from the Earth. Like here's the case where the moon was coming by, and they the source turned off at 70739 here, and they identified the source way out in the polar cleft or polar cusp here. Here's a case where they were getting sources all the way down the geomagnetic tail. This is about 10 Earth radii. So they're way away from the auroral region, which in fact would be where, we're talking about sources. See that N there? We're talking about sources right there if you're talking about auroral sources. As an example, they were looking at the 292 kilohertz channel. If you were talking about sources at the cyclotron frequency, you'd be at like 1.5 RE. You can see that they were getting a much broader spread in sources. 1.5 RE, Earth radii would be right about there, and their sources are pretty far spread. So they weren't on board, clearly not on board with this. So for about 5 years, this debate went on. I think in the literature, Jim would address the latest Goddard paper, and Goddard would readdress the latest Iowa paper. And so this went on for a bit until about 1979, when this paper came out from the Goddard group, and they actually had a set of anomalous observations. So here's an example where the moon is passing by the Earth. This is 30 Earth radii forward, backwards, up and down. So this is a lot of area here. And you can see the moon crossing, right? And the moon should, in fact, by 1540, here's where the moon's edge should be. So fully the Earth has, in some sense, set relative, you've had Earth set relative to the moon from RAE's perspective, yet there's AKR, there's terrestrial kilometric radiation. So this would suggest that the source was out beyond 27 Earth radii. And they knew that that couldn't quite be right. They had no idea why that was occurring. They actually had a handful of these. And what they finally decided is that, in fact, what they were seeing was scattering off of density anomalies in the solar wind, and then the geomagnetic tail, and then the cusp. And so here they sort of, I think the way Mike Kaiser's version of this was that here's their notice of surrender, that we show that they are probably due, they being the radiation, probably due to propagation effects rather than actual generation of the emission at such large distances. Kilometric radiation can be generated near the Earth at auroral latitudes. All right, so, and I still distinctly remember Mike talking about this story, and he said he sent a sign of surrender right up front here, right in the beginning. And I said, and we were eating lunch, I said, well, what was that? He goes, well, it's clear. It should be obvious.
That's the instrument of surrender?
No, here's the instrument of surrender. They sent the three authors, Alexander, Kaiser, and Rodriguez. Yeah, you know where I'm going. AKR. Well, he told me this. So actually, in preparing this talk, this is all pretty funny. This is pretty good. So he was telling me, he said, we surrender. It's an auroral source.
One of those is my student.
Yep, Paul Rodriguez. That's right. He switched sides. Well, actually, he came with you now, right? Maybe he was your columnist in there, kind of working for you. Now, of course, the question is, why is this kind of a debate important? And it really has to do with comparative planetology. I mean, we had emission from Jupiter, and the question was, is that an anomaly? Was Jupiter, or that Jupiter emission alone just an anomaly? Or are we seeing some kind of universality to these planetary radio sources? And you really needed another point, and Earth was that critical second data point. And what we know now is that every planet with a strong planetary dipole magnetic field generates not only optical aurora, but also associated radio emission. And you can, in essence, you can hear the planet's aurora, just like you can see it in the UV. And I would say at this point, you actually have the start of what I would call the transition from Jovian radio astronomy to the science of planetary radio astronomy. And just to kind of show you what it looks like, looking in the back of the book at the answer, this is the post-Voyager spectra from the radio planets. I plot here frequency as a function of flux density normalized to 1 astronomical unit. And every planet with a large magnetic field generates radio emission. Here's Jupiter. What's interesting is only the ones below about 10 megahertz can be detected by space. So Earth, Saturn, Uranus, and Neptune can only be detected from a space-based platform. Of course, Saturn, Uranus, and Neptune were detected by Voyager 2. In fact, Goddard not only discovered AKR, but also discovered Uranus. He was first to see it in your plasma wave system. And there were two radios. There was the Planetary radio astronomy instrument that was up at higher frequencies, and then the plasma wave system down at lower frequency, and Don also detected Uranus. Actually, as it turns out, the folks at Goddard came up with what they call the radiometric Bode scaling law, where you found that, roughly speaking, the radio power from these planets varied directly with the magnetic dipole moment, but also varied inversely with the square of the distance from the sun, because it's assumed that this radiation is solar wind driven at some level. So that's why, even though Uranus and Neptune actually have higher dipole moments by a lot compared to Earth, they actually are out, 20 and 30 AU out, and so you get a big power decrease because you just don't have as much solar wind out there driving them. So you actually can start to see that there's a systematic layouts across the planets. And in fact, even now, people are examining these scaling laws. Now, I'll say at this point in the talk, I had two different directions. I could actually go out to all the planets and discuss all the emissions there, but in fact, I suspect other people are going to be doing that. Instead, I actually wanted to stay at Earth because I think in the 1980s, you did some work that really, I thought, showed just how tenacious you are. I think that you really wanted to get at how that 1 billion watt radio transmitter really worked. You were. I think that was the engineering of you. You wanted. How could Mother Nature conspire to make such a powerful radio source? And not only that, you had the perfect opportunity to examine it. And actually, here it is. Here, if we made it into a TV show, this is what it would look like. You wanted to know about the forensics of this billion-watt naturally occurring radio transmitter. And Jim, I just want you to know, if I ever have to leave NASA, I always have a backup job as a photo illustrator for Star Magazine. Maybe. Well, they're not very good either. National Enquirer. Okay. So you had DE1, and with DE1, you were going to dissect this. You had an opportunity to really dissect this auroral radio source. Basically, DE1 went to 1.09 Earth radii, real close to the Earth, and now to about 5 Earth radii, and had at the time the state-of-the-art radio transmitter, radio receiver, from a few hertz up to 2 megahertz. And Stan Shawhan was the PI until he went to NASA headquarters, and I think you took over for the radio wave instrument. And again, what you had is a chance to really go after the only radio source available, at least for now. Now, at the end of the talk, we'll talk about other opportunities in the not too distant future where we may pass through other planetary radio sources. So you may recognize this. This is our tool. I think Ted has shown this and Don has shown this as well. These are radio spectrograms. This is time on this axis, frequency on this axis, and basically we're just scanning through channel after channel. And you can see as the spacecraft approached the auroral region, the radiation really intensified both at high and low frequencies. And I just want to sort of put in some discriminators here, and hopefully I won't get too technical, but this white line here is called the electron cyclotron frequency. And basically, and this is the electron cyclotron frequency at that location, at the spacecraft location. So this is the local cyclotron frequency. For example, at 540, that cyclotron frequency would be about 30 kilohertz, and so on. And a magnetometer allowed you to draw that line. You use the magnetometer data and then plot that, convert it and then plot that line. This emission right here is called the electron plasma frequency. And it's actually lower than the cyclotron frequency. And this is actually a fairly handy line because if you can find the plasma, if you can identify the plasma frequency, you can actually infer the electron density. And actually, it's a great way. In essence, the plasma is calling out its density to you as you go by in the radio. Of course, here's the auroral hist. Ted talked about this funnel-shaped emission, the saucer-shaped emissions. The emission is generated relative to the auroral electron beams. At low frequencies, the emission cone is really narrow, but at high frequencies, it actually gets very wide. So a spacecraft can actually detect this emission actually long before you actually hit the auroral source itself, the auroral electron beam, the source itself. And the best way to describe these, I kind of describe these waves as trapped waves. They're confined to the medium. So if you won't detect these outside the terrestrial magnetosphere. And what's nice about auroral His is the high frequency limit of auroral His ends up being the plasma frequency. And we'll talk more about that in a second. Of course, the rock star in this is the auroral kilometric radiation. It's a freely propagating radio wave. You can detect it outside the magnetosphere. You can actually detect it at great distances. Again, we could detect the analog from Jupiter here on Earth. But I will say that as you get into the auroral source region, I've kind of blown this up here, and particularly for waves near the electron cyclotron frequency, the radio emission actually changed. It actually gets modified by the plasma and forms what's called an extraordinary mode wave. Out here, the index of refraction for the wave is 1. It's a typical electromagnetic wave. In here, the index of refraction can drop to real low values, slowing the wave down. So you actually have a situation where the waves can actually start interacting with the electrons. So that's an extraordinary mode wave. I just want you to hang on to that. We'll talk more about that in a bit here. Now, sort of along the lines of what Ted was talking about, to characterize these auroral source regions, what you typically had is our electron beams propagating along magnetic field lines. And usually in the region, these electron beams are being driven inward by a field-aligned electrostatic potential. The interesting thing is that the auroral kilometric radiation tends to be generated in low-density electron cavities associated with these electrostatic potentials. So not only do you have a potential, but the potential tends to clear out the electrons. And just let me give you an example of one of these cavities as measured by auroral His. Okay, so this is auroral His in the wideband data. And remember, the upper frequency cutoff of auroral His is the plasma frequency. So if you know the plasma frequency, you can actually calculate the density. And you can see what happens. The density of the electrons is a couple electrons per cubic centimeter, which actually, if you think about it, is pretty low density, but it drops out by about another factor of 100 in these auroral plasma cavities. So you actually have this really strong cavity, really intense cavity deep cavity where the auroral kilometric radiation is generated. So just sort of a cartoon, more of a illustration of what's going on. Here's the plasma cavity, electron cavity as identified by the Hawkeye 1 receiver, Wynne Calvert, who was part of the VLF group here, derived this, made this plot in his 81 paper. So here's your plasma cavity. Inside this cavity, you have an electrostatic potential, and that electrostatic potential is the thing that's clearing the cavity out and shooting the electrons into the atmosphere, downward, to create a discrete aurora. And of course, as you energize these electrons and move them out, they generate auroral kilometric radiation, something like this. So a great example of this, I thought, was a paper by Rich Huff and Don Gurnett back in 1988. And what they did is they used DE1. And of course, DE1 is a spinner, and it has an electric antenna on it. And in fact, when the electric antenna is aligned parallel to the wave's electric field, you actually get a maximum in the signal by the spin, and when it's not aligned perpendicular, you actually get a minimum, and from there you can actually get a direction of arrival. So what they did is they actually plotted the direction of arrival for auroral kilometric radiation down to a surface of constant electron cyclotron frequency. They assumed that there was a direct array path, and that would be like over here. And then what they did is they then traced the magnetic field line down, and there you go. See, here's the auroral kilometric radiation sources, tracing that magnetic field line, boom, right to a discrete auroral arc. And this is using the UV spectrometer, UV imager on DE Lou Frank's instrument. So this is a great way of combining these two, radio and UV data. But more than anything, it really sort of cements that picture of how this thing, how this source region operates. Now, this may be hopefully, now you may ask yourself, how do you actually get this billion watts of power? And Don and Nick O'Meady, actually this was Nick O'Meady's PhD thesis, did a couple papers on this. And there's actually the fancy name, but it's actually driven by the relativistic electron cyclotron stimulate emission process, or really an electron cyclotron instability. And I just want to go through some of this with you. Hopefully it won't be, this probably is the most technical part of the talk, but hopefully I can lay it out in a way that's not too confusing. But as Don and Ted talk about, you have these electrons spiraling around magnetic field lines at about 100,000 times per second. But you also have this extraordinary mode wave. It's this plasma-modified radio wave just generated by galactic background. But when it gets in this plasma cavity, it transitions into this extraordinary mode wave, which has an electric field that rotates like the electrons rotate. And particularly for wave frequencies near the cyclotron frequency, these two can get coupled and into a resonance. And that is actually what they were looking at, is how, and when they're in resonance, the electrons can give energy to the waves, or conversely, in some situations, the waves can give energy to the electrons. Now what I show here, this is from Nick's paper. This is an electron velocity distribution from the secondary small satellite 3, S33. And what I'm showing you here is the electron content in the auroral region when S33 was passing through. This is down, this is a lower altitude. This is this data I believe is from Berkeley, right? Yeah, from Forrest Mosier. And basically what's plotted here is the parallel velocity. So these are electrons moving along the field line as a function of perpendicular velocity, electrons moving, spiraling around here. And what you see is that this is sort of, these are contours, and you can see this sort of forms a mountain with a peak here, and the density of electrons getting lower and lower at higher velocities. Now, as it turns out, there's a well-known hole in this electron distribution. And actually, it's called a loss cone. And it's called the loss cone because when electrons are shot into a converging magnetic field line, those electrons that have a lot of parallel momentum will be lost. They'll actually they'll pass through this converging magnetic field lines and be lost into the atmosphere, forming an aurora. Those with a fair amount of perpendicular momentum or perpendicular velocity will actually be reflected back out. And though that reflected component has this big bite out where you lost the electrons in the atmosphere. Now, as it turns out, plasmas tend to abhor these holes and humps in plasma distributions. They like them nice and thermal and smooth. And actually what will happen is the electrons will want to fill in this hole. But this is a well-known, it's called the Penrose criterion. I actually can read about it in Don's book. He talks about this. The electrons want to fill in this hole. And if you think about it, when you have a fluid like a river moving into the ocean, the river will eventually homogenize with the ocean through collisions. The problem is this gas is collisionless. It's such low densities, it's collisionless. So how do you slow down the electrons to fill in the hole? You actually slow them down through an electric field, right? I mean, electrons are charged particles, and if you have an electric field, you can actually start slowing down those electrons. But remember, those electrons are spiraling around at 100,000 times a second. What you need is an extraordinary mode wave, one of those waves with the E field vector rotating around in the frame of reference of the electron to scatter the electrons into this hole and fill it up. So the electrons are really providing the electric field from the wave is providing the mechanism to scatter these electrons to start filling up this hole. So it's not collisions like it is in the gas here. It's really electrons are doing, or the electric field is doing it, electric forces. Now, as it turns out, as you slow the electrons down, the wave amplitudes grow, right? So, and as the wave amplitudes grow, they actually gather more electrons and toss them into the hole, which means the waves grow even more. And that's really the nature of the instability. The waves grow at the expense of the electrons' energy by slowing down the electrons. So, and that's this electron cyclotron instability. So in a nutshell, and I'll probably get an award for worst speaker because I got an equation up here, but the growth rate for this process, the growth rate is a function of the steepness of the slope. And what Don and Nick found is the region right in here, we have a really steep slope. You can generate just a whole lot of amplification of the background radio emission into, and you can actually transform galactic background into the auroral kilometric radiation. See, the growth rate goes as the steepness of the slope, and then that actually ends up being an exponential term. So you very quickly amplify the background galactic cosmic radiation into the strong signal that you're seeing. So Nick and Don found you could get about 20,000 times gain in about 100 kilometers via this electron cyclotron instability. And really what they did is they actually examined this resonance process in great detail, really I would say unprecedented detail, and they actually even gave you a really nice intuitive feel for what was going on, a scalable tool in some sense. So I would say in the 80s, the Gurnett group was basically dissecting this auroral kilometric radiation process in a way that was really unprecedented. In fact, today, it still remains our primary model for understanding what's going on to create this such energetic emission. Another very interesting study was done in the 80s by Mark Bombeck. This was his thesis, doing 2-point correlated observations of auroral kilometric radiation. IC1 and IC2 actually flew identical wideband receivers. And one of the things you can do when you have two receivers like this is you can actually see how well correlated the various emissions are. For example, you can imagine if you had a small point source and it was giving off a wave front, you would expect IC1 to see it, then maybe a little later IC2, but you would expect strong correlation for a small source. On the other hand, if you had a very large diffuse source, IC1 might be on one side of it and IC2 might be on the other side, and they would have uncorrelated measurements. Well, as it turns out, IC1 and IC2 were seeing strongly correlated measurements even out to baselines of 3,800 kilometers. So for example, here's a picture, here's a spectrogram of the fine structure of AKR from IC2. And you see almost the exact same feature in IC1. Again, same thing here, it's very similar features. And in fact, based on this correlation in the distance between, it suggests the AKR source region for this brightest emission is only 20 kilometers. And in fact, this created a dilemma as to how you could create such a bright radio source in such a small region. So there are two sort of competing theories on this, one by Wynne Calvert, again, who was part of the VLF group, and that is that you had very narrow auroral plasma cavities, and you had the emission amplifying, but you also had what he thought is what you might have is partial reflection of the emission back into the plasma cavity, and then at integer multiples of the cavity size, you can actually get a cavity mode to develop, and you'll get amplification that way. So this would be a propagation effect. In fact, this is exactly how a laser works. You have a stimulated emission process, partial mirrors, and when you're at the exactly an integer multiple of the wavelengths, you get boom, you get very strong coherent emission. But the other possibility being explored even now by folks like Bob Mutel is that you actually are getting an unusual electron velocity distribution called a horseshoe distribution in regions where you have unusually strong parallel electric fields. See, in strong parallel electric fields, you actually generate a big hole right in the center of your electron velocity distribution. And remember, plasmas and these electrons, they don't like these holes, and they want to fill them in. So this is a naturally unstable, strongly unstable to the electron cyclotron instability. In fact, remember I talked about how this is the slope, you get more amplification when the slope is steeper. Well, this is a pretty steep slope in the electron velocity distribution. That's just going to really amplify this radiation right up. So, and why this is important is, again, going back to comparative planetology. We see this at Earth, and the better we understand it at Earth, the better we can understand it at Saturn, because we see it at Saturn as well. This kind of thing. So we see it at other planets. Now, during the 80s, there was a very interesting experiment. Actually, this is what I did my thesis work on, which is during the Space Lab 2 mission by the Space Shuttle, the University of Iowa built and instrumented what was called the Plasma Diagnostics package. And this package was both on the shuttle arm and actually was released for free flight. And almost all the systems were built here at Iowa. And I think, Don, you had 3 radios on board. You had like a high mid-frequency receiver and I think a Helios spare and I want to say one of the IMP spares. It was an IMP? Okay. Okay. But the other thing is the Stanford group had the ability to shoot out an electron beam. So we could actually see, and this was of known energy, so you had a controlled electron beam. So we're actually doing an electron beam experiment. And what we saw was something that we sort of saw in the aurora, not all elements, but some of it, and that is we saw an auroral His emission, not unlike what you see in the auroral region. We did not see the high-frequency radio emission. We didn't see anything like AKR. Really, the plasma conditions weren't right. In fact, I would argue the fact that we knew enough that we weren't going to see this radio emission during the shuttle flight actually tells us something that we sort of trust our models well enough to not be surprised. But it was sort of interesting to see this auroral His. And what we concluded is that the auroral His is actually generated more by the parallel momentum of the electrons in the beam rather than the perpendicular momentum. And actually coupled to the ionospheric plasma via what's called the Cherenkov or Landau mode. So anyway, so I did my thesis on this, and Don wrote really the findings, the original findings on in a paper in '86. So just a lot of fun work there doing that. And of course, going back to comparative planetology, what we saw during the shuttle flight, you know, we now know more about what's going on in the auroral region with auroral His. Right, which actually then translates to the auroral regions at Saturn. So all this stuff sort of interconnects, and by flying these different experiments and doing these different, comparing our data sets, we're understanding what's similar and what's different. Finally, I just want to talk about where, in the near term, we may actually have an opportunity very soon to actually fly through the radio source, strong radio sources at other planets. In particular, Jupiter, heading to Jupiter is the Juno mission. And actually, that mission is going to get within 5,000 kilometers to the cloud tops in auroral regions, and hopefully it'll pass right through these auroral regions. It'll be interesting, again, to compare and contrast what we know at Earth to what's going on at Jupiter. And of course, Saturn, Cassini is near the end of its mission, and it's actually doing one of these proximal orbits where it's actually passing very close to the planet and in between the rings and the planet body itself, and then back out. So it's another comparative planetology opportunity. Again, all we know at this point is the radio source at Earth. So it'll be interesting to get these two and compare and contrast those. And sort of the last topic is sort of the long-term where we're going in planetary radio astronomy. And really, the next step is looking at radio emissions from extrasolar planets. And I don't know if you've been paying attention, but we've actually found other planets around other stars. And actually, in the 1990s, there were only about 10. But the Kepler mission actually has many thousands of these identified. And currently, there are people doing ground-based radio astronomy searches for cyclotron emission from these planets. And so what it really means is this debate over auroral radio emissions and the universe and sort of the possibility that there's a universal aspect to generating these emissions is feeding directly forward to these studies. And of course, why would you want to know about the radio emissions at extrasolar planets? Well, if you're assessing a planet's habitability, you might want like a star-like, might want the planet orbiting a star like our own, maybe Earth-like. You want to be in this habitable zone where you can have water at the surface. It's called the Goldilocks zone. But you'd also want to know if the planet has a magnetic field, since a magnetic field blocks cosmic rays and it reduces atmospheric erosion. And how would you detect that magnetic field? The cyclotron emission, strong radio cyclotron emission. So all of this, all these findings in the late 70s and or the early, the mid 70s, were really very important. Colleagues of ours are using the VLA, very large array, the Ukrainian T-shaped radio telescope, UTR-2. I think that's Philippe Zarka is doing this work. He's our Cassini co-I with us. And then a LOFAR, the low frequency array, is now coming online and making these studies as well. So this is what I didn't cover in the 80s, and it's a lot. And Don, you were so prolific during this period. It's amazing. But yeah, I really didn't get into any of the Voyager. You actually discovered a second radio component, the continuum emission. Again, the discovery of Uranus. I mean, just a lot of great work. It's actually, again, you could spend another hour on this, but I'm already getting. They're telling me I'm out of time, actually. So to conclude, actually, I had a great opportunity to be taught by you and to work with you. But I could also see what you were doing by talking to Nick and Mark and all the other. I mean, we sort of could get a feel for what you were doing just by looking around at what other people were doing. And it's really an amazing, really amazing. You were always very generous with all of us. And in fact, I would say a lot of the Farrell and Gurnett papers could easily have been Gurnett and Farrell, but you were very generous in how you dealt with your graduate students. So I would say the contributions are showing really this axiomatic nature of cyclotron radio sources at magnetic planets that we're now using as a touchstone for exoplanets. And I think in the 80s, you really just wanted to understand that billion-watt transmitter, understanding how that was formed. Just to say a few other words here about you, Don, I just wanted to let you know, I just want to say thank you for all that you've given us. I mean, really, and I don't want to embarrass you, but you really, not only were the tangibles, which is, you got us through our milestones on how to do our thesis, but there were intangibles, like being a role model. You were a spectacular role model. Great citizen scientist, just awesome. You showed us, you really actually built a business. You actually, an academic business that, people thrived on, and you sort of did that. At 25, you're not really, I wasn't thinking about that kind of thing. I just assumed it existed and always had existed, but actually you put it together. And I sort of appreciate that now as I've gotten older. And really, again, you were so kind with us and generous with us you really treat us like partners, even though we were, actually fairly junior.
Well, hey, we worked together.
Yeah, well, see, that is the edit. Well, at Goddard, I work with postdocs, and they have horror stories on how they've been treated by some of their advisors. Advisors refused to sign their thesis because they wanted more work out of them. It's just terrible. They passed, but the guy wouldn't sign.
You're giving me ideas.
But it's just, again, I thank you so much, really, just great. Very, awesome. So anyway, I think that's it. Just one other slide. I mean, I talked a lot about science, but the science couldn't happen without really the hard work and engineering team. So in some sense, I couldn't get into the details of all the instruments, because actually that would be another 2-hour talk. But IMP6, IMP8, Hawkeye 1, DE1, the ICs, PDP, Voyager, and Cassini. Again, Iowa instrumentation on these. So I leave all the instruments as a reference, because I couldn't get into all of that and then do this talk about the science too. Just but really awesome work.
Well, Bill Kerr is the PI on the Juno instrument that's going to go into polar orbit. You mentioned part of that.
I did. That's right. And that's right. Bill is the PI of that. That's right. But still built here is the way I was thinking. So there's still heritage. It's not, still built here. But yep, good. Yep, thanks, sir. So that's it.
Anyway, we do want to leave a little bit of time for questions, and then we want to have a little bit of open mic and leave time for if you go out and find lunch in town here. But if there's a quick question or and I'll actually repeat the question.
Sure.
For the purpose of the recording, but I don't know if there's. Or there were a couple people who wanted to say something. So we also wanted to have a time open mic where people could recount maybe a story or two. I don't know who somebody would contact that. But anyway, we'll have another opportunity for the open mic in the afternoon. I don't know if anybody has a comment or.
Yeah, of course. So I've always questioned about whether protecting the planet from high energy particles was really necessary. I mean, in the case of big outbursts from the sun, I think it is necessary. But if you just had cosmic rays, it seems to me it would advance the rate of mutations without killing the light. And so I don't think it might have to match.
Right. I understand. You know, it could be a source as well as a sink. Yeah, right. So, and even the atmospheric erosion, I mean, there's still some debate amongst the people looking at this whether really magnetic fields really stop magnetospheric erosion. It just erodes differently by going from the atmosphere into the magnetosphere. So there's still a lot of fundamentals about that association that need to get figured out.
Any other questions or comments? Well, we will be reconvening then at 1:45. And there's no, I mean, just on your own for lunch. There are restaurants in the vicinity, but it's not moving it out. And I encourage you to go and enjoy lunch and come back for